we're going to now look at the natural log function. This is the natural log function. I will call it log from here on out. But it's the natural log. So log of base e. Logs were invented to help us. Do not be intimidated by the natural log function or logs in general. They are there to help us. Similar to how if you have a square with an equation and you want to get rid of the square, you use the square root. It's the inverse to the square. When you square root both sides, the square goes away. Isn't that nice? You got that plus or minus. Great. Well, same thing if I had like a square root and I wanted to get rid of that. Well, the inverse to the square root is squaring. That's how e to the x and log x work. Like that. If I have e to the x equal to a number, and I want to get rid of the e, and I just want x. Like I don't want the square root, I just want x, a square, right? Well, I would take the natural log of both sides. It's like square rooting both sides, or like squaring both sides. It will undo what e is doing to x. It will undo the e to the power. It'll just leave us with x. Okay, that's what you need to think of it as. It's just our helpful square root to the square. Conversely, if I have an unknown value inside a logarithm, and I want to get rid of the log, I would not divide by log. It's not multiplication, it's the log of x. So don't divide by log. You would take e to the power of both sides. E to the log x is like squaring the square root versus square rooting the square. Hopefully that doesn't confuse you, but you get x equals e cubed. Okay? So they undo each other. The log of e to the x is just x. E to the log x is just x. Okay? They just undo each other, and you could say, like, the square root of x squared is x, and x squared rooted is x, right? It's like the same thing. So don't be intimidated by it. It's there to help us. All right. We'll talk more about the log function. We need to be comfortable knowing log of e to powers. Since log undoes what e does to a power, the log of e to the x is x, which means if I ask you what's the log of e squared, you'll say it's just 2. Okay, that's easy. I don't need a calculator for that. The log of e to the 300. That's just 300. What do you think the log of 1 over e to the 4th is? You would think 1/4, but it's -4. That's why I asked that question, to set you guys up so you don't make that mistake in the future. Logs will only undo e to a power. This is 1 over e to a power. It's not e to a power, but I can rewrite it as e to a power. So this is actually -4. Okay, brings us to our last 3. I'm going to throw another one in here. These are some that you need to be able to know, especially that one on the right. Go ahead and converse with your neighbors. See if you guys can come up with the natural log of e, the natural log of 1 over e, and the natural log of 1. So these don't have any powers, so we kind of freak out a little bit. But we know there is a power that is just not there but can always be there, 1. We know this could be written as log of e to the negative first, -1. What about the log of 1? Zero. Mr. Moore, why? Because you can write 1 as e to a power. So if I ask you what's the log of e to the 0, you guys all would have said 0. Once I switch it to the log of 1, you're like, I don't know. But you need to know this. This needs to be known. We'll do a couple problems where you will be using that fact. Okay, cool. Now, we will need to solve equations with logarithms in it. We didn't have to worry about e to a power and solving equations using logs, because typically we had equations set equal to 0, and we know e to a power is never equal to 0. So we just kind of factored out the e to the power. We left it alone. We ignored it. But we will find when we do function analysis with derivatives of logs that we will have the natural log in some of our derivatives, and we'll need to solve equations like this. Okay? Don't be afraid. We have our friend e to the power to get rid of the log. It is like square rooting when something is being squared. Sometimes I use carets to denote that I'm like taking it to the power, not multiplying. E to the log of this stuff is just this stuff on the right side. E to the 0 is 1. Add 2, I get x equals 3. Don't go crazy, though, and start taking e to the power of everything whenever you see a log. Isolate your logarithm, like you would isolate a square root, or like you would isolate sometimes an x squared. Add log x or subtract 1 and divide by -1. Then take e to the power of both sides. All right, finish off with the last two. X equals e in this situation. E to the first is e. Get e to the 5th and e to the 1/5. Okay, so be prepared to solve equations with logs in them. Now, that's all pre-calculus stuff, the stuff we just did. That was a review. Now let's get into some calculus stuff. Let's find the tangent slope generator for the log function. Okay, we already talked about last class, e to the x. Its tangent slope generator is e to the x. So like the y's of this were the slopes of it. What is, for log x, the tangent slope generator? They're inverses of each other. They kind of relate to each other. Maybe it's going to be log x. We'll find out. I picked some values, 1, 2, 3, and 4. We will find the tangent slopes of logs using our calculator. Remember, you can graph. This is deceiving, and this is important. It looks like the log function starts at 0, -2, right? Not true. The log function will go all the way down towards -infinity. Okay? E to the x, always positive. Inverses will always be reflected over the y equals x-axis. We'll talk about more y. We'll talk about y more next class. Why inverses are reflected over the y equals x-axis. Okay? So, since e to the x, the y's were always positive, we will not be able to plug in anything but positive values into the log function. Log function has a very restricted domain, only positive x's. Why is that the case? Another reason why that is the case, why I can show you why you can't have the log of 0. If I asked you, what value do we take e to the power of to get 0? You would say you can't. This is why the log of 0 does not exist. Same with like e to an x equals a negative number. It doesn't happen. That's why you can't take the log of a negative number. Okay? Okay, great. But let's find the tangent slope generator. All I can do is find some tangent slopes. So at 1, at 2, at 3, at 4. And maybe by looking at those, I'll be able to understand what the tangent slope generator would be. All right, ready? Remember, we can go second calc, dy dx. This is number 6, tangent slope. Plug in your x value, press enter. Okay, when x is 1, my slope is 1. All right, so maybe these are the y's. The tangent slopes are the y coordinates. Maybe these are the x coordinates. I look at 2, second calc dy dx at 2, and it's not 2. It's a half. Okay, that's interesting. Let's see. Second calc dy dx at 3. I get 0.3. Okay, that's 1/3. Second calc dy dx, we could probably guess. I hope it's 1/4, or else I don't know what it's going to be. Yep, you get 1/4. So whereas e to the x had all about y's for the tangent slope, log x is all about the x's, but not just x's. It's 1 over the x. It's the reciprocal of your x value. So this, my friend, is the tangent slope generator. This is something you will now have known as part of your derivative rules arsenal, that the tangent slope generator for the log function is 1 over x. Now, my friends, something seemingly easy to me that ends up being difficult for students. Please write the equation of a tangent line. 2, f of x equals log x, f, x equals e squared. You got it? No. No? Oh, man. Probably struggled on that quiz question now. The 2 ones about the equations of the tangent lines. Okay, good. Well, these are not hard either. I don't know why. This is the function. This is its tangent slope generator. Okay, good. Please check your answers with a neighbor. Good. Y minus, if I plug e squared into f of x, f of e squared is log e squared, that's 2, equals f prime of e squared would be 1 over e squared times x minus e squared. Not that bad, right? Okay, good. Do the same thing at 2 now. I need somebody to ask me the question that I'm looking for. What's the question that I'm looking for? What's the log of 2? I don't know. Just write it in log of 2. Okay? The ones you should know are the log of e to any power, which includes the log of 1. You need to know that. But if you're given the log of any other whole number, you're just going to leave it like that. And that's okay. It'll be part of your answer. Multiple choice or for your response. Totally fine. Okay, moving on. Not all of our derivatives are going to be that easy. Here are other functions that include logarithms that are not just log x. The derivative, y prime, of log 4x is not 1 over 4x. Unfortunately, that's not right. Just like the derivative of log of x to the 4th is not going to be 1 over x to the 4th. Unfortunately, that's not right. Because you need to follow your rules. Okay? We have to care about our rules. And when I asked you what is the derivative of sine 4x, you told me it was not cosine 4x. It was cosine 4x times 4, because you remembered your chain rule and the O's and the I's. And you remembered, oh, okay, the outside is the sine of, the inside is the 4x, and you did not forget to multiply by that 4. It will be the same with the log function, just like it was with the e to the power. Okay, so please, don't forget your O's and your I's. Your outside in this case, this is not multiplication. It's not log times 4x. Please, please, please don't say, hey, we should be using the product rule. No, this is not a product either. Sine of 4x is not a product. It's a composition. Log of 4x is not a product. It's it's a composition. The outside is the log. The inside is the 4x. The tangent slope generator for log x is 1 over x. The derivative of log of parentheses is 1 over parentheses. The derivative of 4x is 4. Remember, we multiply our composed derivatives. I get 1 over 4x times 4. Huh, look at that. This is 1 over x. Okay, try the one on the right. Log of x to the 4th. It will not be 1 over x. Close to it. Okay, we end up with 4 over x. We got 4x cubed divided by x to the 4th, 4 over x. This one's very similar. What you'll find if you do enough of them that you'll just have 1 over the stuff times the derivative of the stuff. And typically we will write this so that the 2x plus 3 is above the x squared plus 3x. Don't simplify anything here. Don't cross out x's. Don't think that you can cross out the 3's, okay? We have addition, so we are done simplifying. Just write it like that. If I could factor and make these sums products, then maybe I could simplify, but I can't, so don't try to do anything funny. Okay. The next one, notice the inside is a quotient. Do you remember the quotient rule? I hope so. We practiced it, I think, with the e to the power. But we did not do much of it during the third unit, function analysis unit. Derivative of the top is 1 times the bottom, minus the derivative of the bottom is 1 times the top, all over the bottom squared. Fortunately, that can simplify. O derivative, I derivative would be 1 over, now this is interesting, it would be 1 over this fraction times that derivative 1 over x plus 1 squared. Now we know 1 over this fraction can be written as the reciprocal. I could write this as x plus 1 over x. So I'm going to do that. And then the next thing I notice is that, yes, we have multiplication. Since I have multiplication, I can simplify those x plus 1s, and I get a nice, simpler looking derivative here. 1 over x squared plus x, or x times x plus 1. I like to leave things factored when I can. But don't worry if you didn't. Okay, bottom, the next two. I'm going to give you 2 here, and then we'll just do 1 here. Actually, we'll do 2 over there. I need more space. Throw that one in there. Y equals 3 log x over y equals x log x.
Wait, like a fraction?
Like that. Cool?
Are those 2 different?
These are 2 different ones, yes. 2 different ones. Okay? Now, recall, if I asked you to take the derivative of y equals 3 sine x, did you have to use the product rule? No, with emphasis. The derivative was just 3 cos x, right? Because if I did use the product rule, the derivative of 3 is 0. I'd have 0 sine x plus the derivative of sine x cos x times 3. Oh, that's just 3 times cos x. The constant multiple rule is in play here. If you have a constant in front of a function, you can just leave the constant alone and multiply by the derivative. So what do you think the derivative of 3 log x is? 3 over x. Very good. 3 times 1 over x. Do we see that? Don't make things harder than they have to be. Now you might think, oh, this derivative is x over x. It's 1. Nope. It's not a constant. It is a function. We have to use the product rule for this. No product rule. Yes, product rule. Please take the derivative of x log x. Leave it right there on the desk. It's fine. We get log x plus 1. Yes, quotient rule. Derivative of the top times the bottom. Have a good one. Minus the derivative of the bottom times the top, all over the bottom squared. 1 minus log x over x squared. We'll see that one again. Fantastic. That's Unit 2, kind of derivative rules with logs. We remember all of our derivative rules. We remember higher order derivatives. This being notation for the third derivative. I'm going to go quickly through this. You have to understand the O's and the I's. Whenever you have the O's and the I's, we're going to have the derivative of the inside. So I got negative 2 sine 2x plus, this would be 1 over 2x times 2. Take the derivative again. Remember the notation is d squared y over dx squared because you're taking the derivative d times d squared y, dx times dx squared. This would become negative 4 cosine 2x. Remember the derivative of 1 over x. Rewrite it as x to the negative first. It'd be negative 1x to the negative second. Take the derivative again. We'll get d cubed y over dx cubed. This would be a positive sign, 2x. The 2 would be multiplied by the 4 to give me positive 8 sine. Derivative of negative cosine is positive sine. 2x. This turns into x to the negative second. Its derivative would be negative 2x to the negative third. That negative and that negative would cancel. Okay, so just something you may see moving forward. Just a reminder of higher order derivatives and chain rules and stuff. Okay. Back in Unit 1, we talked about piecewise functions and being continuous. I will give you piecewise functions with e to the x and logs. So let's recall these piecewise functions to ensure continuity. Well, ensure that both individual pieces are continuous when you're using x. Yeah, x squared minus 2x, that's easy. I'm a little bit worried about the 2 log x because it has that like domain where you can't plug in x's that are less than or equal to 0. But I'm using x's greater than or equal to 1, so this is fine. All I need to do with these piecewise functions is check to see if the first piece meets up with the second piece where we leave one and we pick up the other. So let's do that. Pretty easy, except for this little bit. If you don't know what the log of 1 is, you're not going to have a good time finding A, especially if this is a multiple choice problem. You need to know what the log of 1 is. You need to know that 1 can be written as e to the 0. So you will remember that the log of 1 is 0. And then you'll get A. That was back in Unit 1 when we just talked about things being continuous. They just needed to connect. That was nice. But then in Unit 2, we talked about things being differentiable. What were the conditions that ensured that a function is differentiable? Discuss. The derivative has to exist everywhere. For a derivative to exist everywhere, the function must be continuous and it cannot have any sharp points. We need to ensure that by making sure the first piece and the second piece meet up, just like the last one. I get a equals 3. And we need to make sure that the slopes, when they meet up, connect, so that you don't meet up and create a sharp point. You meet up and it's a nice smooth connection. I need to make sure that the derivatives of f little 1 and f little 2 at 1 also equal each other. I get 2ax. I get 3 plus, okay, this is just a number. Since it's just a number, I do not have to use the product rule. B log x has a derivative b over x. This I could plug 1 into because I'm trying to find the tangent slope generator at 1. And I know what a is equal to. Turns out b is the same as a, just for this situation. Fantastic, fantastic, fantastic. Well, we're done with Unit 1. We're done with Unit 2. Let's move into Unit 3, some function analysis. Let's figure out when, let's cross off the second derivative right now. When is this function increasing? When does it have maxes or mins? Okay, let's go. We got to do a sign analysis of my first derivative, right? F prime. Got to figure out when f prime is equal to 0 or undefined. That's when signs could change. That's when I could go from increasing to decreasing or vice versa. I need to be able to take the derivative. We already did this. It ends up being 1 minus log x over x squared. Okay. Now, got to find those potential sign change locations. 0 undefined. Undefined usually we forget about because we always have like derivatives that don't have denominators. But I got a denominator here. So I want you to, be cautious and be wary. Hey, x should equal 0. That's important. It's actually important for another reason, which could have prefaced this. This function has a log in it. We are not allowed to plug in 0 or anything negative into that function. So in reality, when we are doing our sign analysis of f prime before doing anything, we could have said, oh, wait, we need to start at 0. Don't look at 0. Don't look to the left of 0. We have a starting place. Kind of did this a little bit when we talked about trig functions, so that we didn't find like all the maxes and mins. Start at 0. So 0 important, but yeah, it was already important. The other one comes from 1 minus log x. The numerator set equal to 0. Please solve that. You've already done it, so let's just do it really quickly again. Isolate the log. Use your friend, the inverse, which will undo what the log is doing. Okay, plop e down. Great. Now this is like unfamiliar to us. We're used to like numbers, at worst square roots, but now I got e's. Here's my derivative. We are used to plugging in values bigger and smaller. Okay, sure. I don't know, 10. Well, here's the problem. I don't know what the log of 10 is. I can kind of figure it out. But it doesn't help me. It won't help you guys either. So don't pick 10. 10 is not a good number to pick. Discuss with your neighbors. What would be a good number to pick that I can plug into this and it will work out nicely? Yes, yes, yes. E to a power. So if your derivative has log functions use an e to a power as a test point. So don't plug in 10, plug in e squared, e cubed, e to the 10. Don't plug in 2, but you could plug in 1. Why could I plug in 1 but not 2? E to the 0 works. You could also do e to the negative first. 1 over e, it's a fraction. E to the negative second. Sure. You could also plug in 1. Fine. Now watch what happens if I plug in e cubed. Now, remember, e to any power is positive, but also I'm squaring in the denominator. My denominator is positive, so like I don't even have to worry about the denominator. Forget about the denominator. It's just positive. Let's worry about the numerator. 1 minus log e cubed. 1 minus 3. Negative 2, it's negative. It's a negative divided by a positive, it's a negative. E to the negative second. 1 minus log e to the negative second. 1 minus negative 2. Positive. Okay. That means x equals e is a max, and we are increasing from 0 to e. Now, let's do both. I'm going to change this from increasing at a decreasing rate to decreasing at an increasing rate. Because it doesn't happen the other way around. Sign analysis of f prime and f double prime. Okay, so let's just do this as an example. We already took the derivative of x log x. We get 1 times log x plus 1 over x times x. That's log x plus 1. We can set that equal to 0. I get log x equals negative 1. Now, we haven't seen something like this. Don't be afraid of log x equals negative 1. You might be thinking, oh, that doesn't exist. It's like, no, you can't plug in a negative into a log, but logs equal any value, any y value. We get x equals e to the negative first. Start at 0. We have 1 over e. You can plug in e squared. You'll get positives. You plug in e to the negative second. You'd get log of e to the negative second plus 1. Negative 2 plus 1, that's a negative. All right, so we know when we're decreasing from 0 to 1 over e. Let's look at the second derivative. It's pretty easy in this case because it's just 1 over x. So we think that x equals 0 is the important point because that's when it's equal to 0, but it's already an important point. But what we will find is that the function is always going to be concave up. So when we are decreasing at an increasing rate, that's when f prime is negative and f double prime is positive. That'll be from just 0 to 1 over e. We are concave up everywhere. And we're going down and then going up. We have a min at x equals 1 over e. Cool. Some more. This one's not great. I feel like I can change this. Why don't I change this from x squared plus 7 to x squared plus 4. Usually this works out nicely. Let's see. F prime is positive and decreasing. So I'm looking for F prime positive, F double prime negative. Let's see if that happens. Okay, the derivative, be careful. The derivative of the outside times the derivative of the inside gives me 2x over x squared plus 4. If we set this equal to 0, 0 is the only interesting point. So 0 is already an interesting point. I can't solve this denominator equal to 0. X squared plus 4 is never negative. It's never 0. It can only be 4 or above. So let's see. F prime is positive everywhere. Cool. When is F prime decreasing? So when is F double prime negative? All right. Now notice, my first derivative got rid of the log. Now I just have a quotient rule situation. The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And we will have an equation to solve. The top equal to 0, the bottom will always be positive. I get 2x squared plus 8 minus 4x squared over x squared plus 4 squared. I can solve this set equal to 0. This is negative 2x squared plus 8 over x squared plus 4 squared. This will be x squared equals 4. X will equal plus or minus 2. Now, plus or minus 2, sure. Understanding, oh, actually plus or minus 2, important. So this is good. You got to think that like x's have to be bigger than 0, but actually x's could be anything, because when I square x, it's going to be a positive. So I'm actually not doing this right, because inside here will always be positive. I actually have to look to the right and the left of 0. So this would be a positive, but to the left of 0, that's negative. And now if I look at plus and minus 2, let's see. I'm going to plug it back into this, knowing that the denominator is always going to be positive. If I plug in 3, 9 times negative 2, that's going to be bigger than positive 8, so that's a negative. I plug in 0, positive 8. I plug in negative 3, that's a negative. So that's F double prime. So very interesting. Positive and increasing would be 2. Let's change it to positive and decreasing would be 2 to infinity. And that'd be my answer. But we can also see when it's positive and increasing. It's got a min, it's got points of inflection, all cool stuff. Why don't we look at this for fun? Let's get rid of this stuff. And let's look at log x squared plus 4. I think I have a min at 0. I think it has a point of inflection at negative 2 and 2. Isn't that great? At 0, I have a min. At 2, zoom in right at that. I should be able to see that point of inflection a little bit clearer if I zoom in. We are concave up until 2, and we will switch to concave down right there. Phenomenal. I'm going to change this one too. Find the rate at which f of x is decreasing. This is like a wordy problem that I want us to be prepared for. So f prime is 1 over x minus 2x, okay? Now, we want to find the rate at which it's decreasing. So let's think about this. If I looked at when this was negative, that's when f is decreasing, and finding the value, like f prime of 3, 1/3 minus 6, that's minus 17/3. That is the rate at which f is decreasing. Yeah, that's it. This is the rate at which f is decreasing. I'm overthinking it. There's another way I could state this when we're talking about what is the rate at which f is decreasing, and we look at a second derivative. But I can't think of the right way to do that right now. So this is fine. You won't see much on your homework with that. We finished off with some table problems. So we are just going to be using our derivative rules. Now I know when we see stuff like g of x or f of x that we forget about our rules. Some people will tell me that, like, if you're trying to find f prime of 1, that f prime is going to be like g of x over x. But that's not true. Okay? So with all of these table problems, when we all have g's and f's instead of just like x's and x squareds, don't forget your rules. Derivative would have to be using the product rule. The derivative of the first times the second plus the derivative of the second times the first. We'll plug in information. F prime of 1 would be g prime of 1, which is 3, times log 1, which is 0, plus 1 over 1 times g of 1, which is 2. So this is just 2. And finally, this one, very important, log of g of x. You would have to not use the product rule in this case. This is a chain. The log is the outside, the g of x is inside. The derivative is not. The derivative is 1 over g of x times g prime of x. So make sure we understand that. Plugging in 2, we get 1 over 3 times negative 6, or negative 2. All right, that's it. We covered it all. Good luck on the homework. That's logs and derivatives.